quantum mechanics is a branch of physics that describes the behavior of particles at quantum level. So quantum mechanics is a branch of physics. That's why you notice a lot of physicists do have a good knowledge of quantum mechanics because this is something they have covered. But just as an aside, I would like to mention that not having a physics background should not hinder or make you doubt yourself in terms of wanting to learn quantum computing. I do not have a physics background. Probably maybe the first 2 years of high school, I did physics. But outside of that, the physics that I know is the physics that I would learn in my quantum computing journey. So even if you don't have a physics background and quantum computing is something you're passionate about, I would just like to encourage you that you can still manage to thrive in this field. You know, if you desire a career in it, you can still manage to do that like I did. My background is in IT. Not, I would call it zero physics background, but I still managed to thrive, and you can too. So the three key principles in quantum mechanics, you have superposition, entanglement, and interference. So superposition is what we already, described, saying that, it allows qubits to exist in a combination of states representing both 0 and 1 simultaneously. Entanglement refers to the correlation between qubits even when separated by large distance. And then interference refers to the intrinsic behavior of a qubit due to superposition to influence the probability of it collapsing one way or another. So this is the part where we talk about wave-particle duality. So these principles provide quantum computers with the ability to process information in a fundamentally different way than classical computers. So now to just, explain in a bit more depth, we already talked about superposition, interference, and entanglement. So I'd just like to, describe those in greater detail. So like I mentioned, superposition it refers to a combination of states we would ordinarily describe independently, right? So classical analogy of this, we could say you're spinning a coin. I had a coin before, but anyways, I can't find it. But let's say we are spinning a coin, right? So when you're spinning a coin has two sides, heads and tail. So in the classical, you can never have a point where it's those two states at the same time. It's either it's heads or it's tails, no in between. But with quantum, we are saying there is a point, like when you spin a coin and it's circling around, it's neither heads nor tails, right? It's in like that state it's in is called a superposition, right? So until you either, flatten it so that it falls onto one of the sides, you do not know what state it's in. So that is what we can describe as superposition. So most famously, superposition has been described using Schrodinger's cat, right? So where it's described as the cat is dead but alive and alive but dead. So what does Schrodinger's cat experiment say? So Schrodinger got a cat, right? He put his cat in a box. In that same box, he also put poison. So, and then he sealed the box. So if you were to walk in a room where he left his box, the cat is both dead but alive because you don't know if it ate the poison or not. So it could either be dead or it could be alive. So unless we open the box, which in this case, in the quantum, case of things like I mentioned earlier, that would be measurement, right? So unless you open the box, which is, carry out the measurement, you don't know if the cat is alive. So unless you open the box and the box is just closed and we know there is the cat in there and the poison in there, the cat is in a superposition, right? The cat is dead but alive and alive but dead because we don't know. So that's why I put this meme on the bottom right corner, which says, Schrodinger's cat wanted dead and alive, because it's in a superposition of being both dead and alive. So, that's why it's written like that on the flyer where it's wanted. And then the next quantum mechanics law that we'll talk about is entanglement. So entanglement is the ability of quantum particles to correlate their measurement results with each other, right? So it refers to when particles remain connected so that actions performed on one particle affect the other, even when separated by great distances. So this is what Albert Einstein referred to as spooky action at a distance. So classically, we can describe it as this, assuming I have a pair of gloves. So there's the left one and the right one, right? I have my pair of gloves, and then I decide, let me send Dorcas another one of my gloves. Dorcas is in Ghana, I'm in Zimbabwe, so definitely a few, maybe 6 or more hours flight away. So there's already great distance between us. But as long as I know that, because these two are correlated, the gloves are correlated, as long as I know that the glove I have is for the left hand, then because the two are correlated, we are certain that the glove that Dorcas has is for the left hand. If she's also certain that the glove that she has is for the left hand, then it means the one that I have is for the right hand, because the two are correlated. When you have a pair of gloves, they are two, one for the left hand, one for the right hand. So that is what is described as spooky action at a distance. And in general, that's entanglement. Of course, you learn about the quantum computing side of it, but today I'm mainly focusing on just you getting the general understanding of things, such that when you get to the programming and mathematics of things, you know where we are coming from, which makes it more interesting. And then we have interference. So interference, it's a phenomenon where we have two waves superposed to form a resultant wave of greater, lower, or same amplitude. So the resultant of the two or more waves at a point. So this is what it will come down to, the little picture at the bottom. So we have wave X, we have wave Y, and then we have resultant wave Z. So it could be constructive interference or destructive interference. So those are the three main fundamentals of quantum computing. So you'd notice that these are the three things that will somewhat occur most often, or those are the things that will affect maybe your code to some way. Like it could be something that's on the behind part of things. So linear algebra, I'm just mentioning this so that even after this you could just, if you want to refresh your memory on it, you could, so that maybe what are the things that you might need in learning quantum computing. So linear algebra is a fundamental part of this, because you use it for explaining objects such as lines, planes, or rotations. So you notice these are the things that you'll be using on the block sphere, for example. So it's just a gentle reminder that your linear algebra should be up to speed. It's not a very heavy mathematical thing, but it's good to also know it. So after all is said and done, we have talked about superposition, we have talked about interference, we have talked about entanglement, we have talked about the block sphere, the qubit, the bit. So what then is quantum computing? Because yes, I've been blabbering about all these things, but what then is quantum computing? So quantum computing is mimicking the way in which nature computes, right? So the use of quantum phenomena such as superposition and entanglement to perform computation. So those are the three phenomena that we mentioned: superposition, entanglement, and interference. So Richard Feynman also once said that nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. So that's why you notice that in some of the areas of application, we are going to mention things like chemistry, simulating drugs, because some of these things are nature. Nature is everything around us. It is not classical. It's termed to be quantum. So for us to have a better understanding of it, we should do it the quantum way. So I'm not sure if there are any okay, I was just checking if there are any questions up to this point, because I would like to talk about the areas of application of quantum computing, because these are the things that you'd want to have an idea on, given that you'll be working on quantum computing for social good. So the areas of applications that you could use it for the social good. So quantum computing has the potential to revolutionize various fields. So I'm just okay. Before I talk about the areas of application, I just wanted to mention the last line on this slide. It says, under the fundamentals of quantum computing, this unique property allows quantum computers to perform computations in parallel, potentially providing exponential speed up for certain problems. There's a reason why I highlighted potentially, actually put it in bold, potentially, and also certain problems. So I've gotten asked this question, at different platforms, about quantum computing, or if it will destroy this, or if it will build that. The reason why it says certain problems is because they are like, quantum computing is just like a coin. There are two sides of a coin, heads and tails. So it means it has its pros and it has its cons also. So at the moment, given that it's still a work in progress, there are certain problems that, they have been worked on and proven that, okay, on this certain problem, solving NP hard problems, for example, a quantum computer is better. But when solving certain problems, a classical computer is better. So please take note that, yes, quantum computing will revolutionize various fields, but it will not solve all the world's problems. I mean, it will help solve some, and we are working on it solving more and more and more problems as we go, but it also has its shortcomings. So I wanted you to, get into this field with an informed mind. So under the areas of application for quantum computing, it can be used in cryptography. So it can break classical encryption algorithms, posing a challenge to secure communication. So you'd notice that's why quantum computing is being used in security. Maybe something that you learn further on, but there's an algorithm in quantum computing famous. We have Grover's algorithm, which is famous. We also have Shor's algorithm. There are more algorithms, of course, but Shor's algorithm is one that poses the greatest threat to cryptography and encryption, because it works in more or less quantum key distribution. So that is an area of application for quantum computing. We have quantum computing being used in optimization. So quantum algorithms can provide efficient solutions for complex optimization problems, such as portfolio optimization or logistical planning. So maybe an example I could give is earlier in the year, I attended the New York University Abu Dhabi hackathon, quantum hackathon for social good. And as I was a mentor at the hackathon, so some of the problems, maybe to be more specific, the problem that my team worked on was under optimization. So it was in machine learning, and then, so it was optimization. So what we came up with was, if there was a natural disaster that happened in UAE, we wanted to put safe zones where people could access, healthcare, medication, water, in cases of an emergency. There are certain basics that one might need. So we wanted to create optimal locations and optimal routes for people to be able to access help. So we wanted it to be a case whereby people from the health department have an app that can help them find the most optimal route to an area where the natural disaster has happened, so that people could get help as fast as possible. So that is just an example. And then in quantum computing can also be used in drug discovery, which is something that I mentioned earlier on. So in drug discovery, quantum computing can accelerate the simulation of molecular interactions, leading to faster and more effective drug development. It can also be used in material science to aid the design of new materials with, desired properties such as superconductors or lightweight alloys. It can also be used in artificial intelligence. For example, quantum computing can enhance machine learning by improving pattern recognition and optimization tasks, which is something that I've also just mentioned earlier in terms of optimization tasks. So other areas include financial modeling. Where I work as a quantum developer and researcher at Stafford Computing, we do most of our work is in finance. So that would mean machine learning, using quantum machine learning in the side of finance. So that is, an area of application that is currently being used in real world. We have better batteries, similar to what would happen in the quantum chemistry side of things, cleaner fertilizations, which is quite good, given that, for example, in areas in Africa, we are a really heavily, farming, agriculture type of continent. So cleaner fertilization or cleaner fertilizers would be very good for our crops and, our food shortages. We also have traffic optimization, weather forecasting and climate change, artificial intelligence, solar capture, electronic materials discoveries, and there are a few more that are on that link. I will share the slides. So those are the areas of application for quantum computing. And then, like I mentioned, that quantum computing has its advantages, but it also has its challenges. So I'd just like to mention a few of its challenges and maybe what I feel and think is the future direction of quantum computing. So despite the promising potential of quantum computing, there are still several challenges that exist. So one major challenge is maintaining qubit stability and reducing errors caused by noise. So of course we have error correction and noise mitigation to help this and help address this issue. But qubit stability is difficult in that maybe I should have put a picture up, but yeah, I will add it to the slide. But a quantum computer, it exists in a very delicate environment. If you notice, if you had to Google it right now, the picture you get is of something that looks more like a chandelier, and then maybe something right around it, right? So that coverage is to maintain certain temperatures, right? So it exists in a very delicate state. So a little bit over, a little bit under, it causes a problem. So maintaining qubit stability is a bit difficult. So once there is that, then it means there are errors, and then you don't want results that have errors. You want the more accurate the results, the better, of course. And then scalability, as quantum systems with more qubits become increasingly complex to build and control. Of course, there is collaborative efforts between academia, industry, and governments to advance quantum technologies and overcome these challenges. But because the initial quantum computer said 2 qubits, then 5 qubits, then it got to maybe 20 qubits. The last in the last IBM hackathon that I attended, we used a 127 qubit. I think there's also a 433, but you could also just check the IBM, they have their timeline well written out on the year and, the qubits that they are working on and would like to release. So those are some of the challenges of quantum computers. So these are also things to think about when you are coming up with a solution. And, because you want to look at all sides. So if you come up with a solution, you should look, okay, if there is, noise, how can I help with this? Of course, there's error correction, there's error mitigation. So this helps with the noise. So it means something that is not solely impossible to overcome. And, so I think the future direction of quantum computing involves a lot of research and development to build practical fault-tolerant quantum computers and explore new applications across various industries. So someone recently brought up the subject of something along the lines of forensics. And, she was asking me, I think it's called forensic analysis, or but I think it's that field that, okay, I've seen more of it in thrillers and series and on TV, where someone dies and there's all this forensic investigations of what was the cause of death. And so it's more on the police investigation side of things. But she was asking about are there any areas, or is there any work in quantum computing being done in that field? And to my knowledge, I told her no, because I don't know any. They might exist or not, but like I mentioned, of course, I don't know everything. But so it just got to me that there are other new areas of applications across various other industries where quantum computing could be helpful. I mean, in those fields, if they are going to be analyzing images of whatever they are carrying out their forensic investigations on, it means that there will be need for quantum machine learning, for better image processing. So you notice there are so many areas of applications in different fields that you yourselves can also, discover and explore. So, the good part about joining now, which I'm excited about, for all of you to be joining, is because, we are still, at the early stage. Like I mentioned, there's still a lot of research going on. There's still a lot of development. So there is, a lot of room for you to contribute. And, in the next 100 years or so, someone will also be, giving a lecture and quoting your own quotes that you would have come up with and your own discoveries in quantum computing. So maybe I just tried to come up with some of the most common questions in quantum computing for someone who's starting. So what are the skills one might, ask, so what are the common skills that one might need to thrive in quantum computing? So, to understand quantum mechanics as a first is good. And, the quantum mechanics that is the foundation of quantum computing, we have already covered today. So there is no, out of this world other quantum mechanics. Of course, you could learn these things in depth. Of course, there are other areas also in this regard that you could also learn about in terms of quantum mechanics. But I mean, the three most important phenomena, we have covered them today. Hopefully you understood them to some extent. It took me some time to get them, but I'm hoping you guys also got them. And then you also, so it's also good to know a bit of programming. Of course, the programming that you'll be doing, it's not like, you're programming a whole computer, programming how Zoom is supposed to work. No, it's just, some basic programming so that you'll be able to, implement the quantum gates that you want to use, because you'll be using them, how to measure them, and how to then analyze your results or have your results in a readable format, and linear algebra, like I already mentioned. So it's also good that you know some linear algebra, because you'd notice on the block sphere that's the matrices and vectors. Those are things that you need to know and have an understanding, as they will help you in your computation as well. So yeah, these are the references to the information I used. And yeah, so this brings me to the end of my presentation. If there are any questions, please feel free to ask questions. If you also want to add something that you think, oh, I think people should know this is the time. You could either type it in the chat or raise your hand. But this is the information I had to share with you guys. So this is just an introduction, the basics, the less heavy stuff of quantum computing that I thought is important for you guys to know before you get into in depth with this. So this concludes the introduction. Maybe I'll just stop sharing my screen and then I'll check if there are any questions or contributions. But otherwise, Dorcas, this concludes my share of an introduction to quantum computing. I'm hoping that people really understood the fundamentals, because once you have the solid foundation, the challenge that Dorcas mentioned, then you'll definitely be able to thrive. I will also just share my email. I've shared my LinkedIn, but I also just share my email. Dorcas has the slides, so she'll communicate and share those with you. So feel free to also, if you have follow-up questions, feel free to then reach out to me afterwards. Thank you, Dorcas.
Thank you, Lauren. That was a very wonderful presentation. And I might say you have very nice comments coming from people. I may share that comment with you later. People are so excited because, someone is saying this is their first time actually getting that concept, the basics. So I think it's good. It's been wonderful. And if you're excited about a presentation and you followed up, we'd like you to show a thumbs up in the chat, just to show that you are still with us. Great. So let's have more thumbs up, just to know you are still online with us and you are really appreciating the lecture. It was basic, Lauren, and that was wonderful. Someone is asking here at my end, is that a professor? Like, wow. Okay, that's wonderful. It's great to have you all joining us for our first session today. Just be expecting more. This is just the beginning, and we think it's basic, like she mentioned. You don't need to do much. You don't need to be a physicist. You don't need to be a computer scientist. It's for everyone, and everyone can do it. You just need to be committed and consistent as well. So thank you all. I would like to take a snapshot. So if you don't mind, kindly put your videos on for us.